Good afternoon, morning, or evening. My name is Paul Beckwith. I'm with University of Ottawa and Carleton University. My website is paulbeckwith.net, so please check it out. Also, if you just Google YouTube Paul Beckwith, you can find many of my videos. So the big question for humanity, for everybody on the planet, because they'll be affected by this, is will we have zero Arctic sea ice by 2020 or earlier? Okay, so I'll try to answer that question in this video. So, first of all, some definitions. The sea ice area is defined as the area where the concentration of the sea ice is 100%. So there's no open water regions, right? The ice could be broken up, but it's compacted. There's no gaps. The sea ice extent is defined as a region that has at least 15% of the sections occupied by sea ice. Okay, so it can be 85% open water, 15% sea ice is included in extent. So it's equal to the area, which is 100% sea ice, plus the regions with ice between 15 and just less than 100. Okay, now sea ice volume. It's the total volume of sea ice, obviously. Right? You get it by multiplying the area by the average ice thickness, but you really need to add the volume of all the separate floating pieces, or at least estimate them, to get the total sea ice volume. The first blue ocean event. Okay, I have been calling it this for many years, blue ocean event, using this term. Not sure if I originated that term or certainly started using it after it was originated. If it wasn't me, I don't remember. But it's the occurrence of essentially zero sea ice in the Arctic Ocean. Okay, a common practical threshold is when the area is less than 1 million square kilometers, or the extent's less than 1 million square kilometers, depending on the definition. Fast ice is attached to the shoreline. It doesn't move. It's held fast. Okay, so there might still be some fast ice left when the sea ice is all gone, the stuff that's all floating. Multi-year ice, if the ice lasts a melt season through a melt season, then it becomes multi-year ice, second year, third year, etc. So first year ice is weaker because it's got a lot more salt in it. Mechanisms for Arctic sea ice loss, okay, just logic 101. The ice can melt from above. That depends on the air temperature. Higher air temperature, more melt. The albedo or reflectivity of the ice surface. Darker surfaces absorb more sunlight, so they'll heat up more. Cloud cover will reduce the solar radiation, reducing the melt. Okay, they'll affect the amount of sunlight reaching the ice. The number, size, and depth of meltwater ponds. So when the ice is melting on the surface, you get water ponds forming. Those are darker, so they'll absorb more energy. So if there's more meltwater ponds, the ice will melt more on the surface until the water drains through the ice and is released from those meltwater ponds. What are the physical characteristics of the ice? Is it contiguous, continuous? Is it cracked? Is it broken into small pieces pushed together? Okay, all of these things greatly affect the total surface area of all the pieces. A lot more smaller pieces will have a much larger surface area and therefore will have faster melt. So the strength of the ice, first year has many brine pockets, it's weak. Multi-year is fewer brine pockets and is stronger. Okay, so all those things affect the melting from above. Melting from below depends on the water temperature, obviously. The amount of vertical and horizontal mixing in the water column, because if you get the ice melting from below, it'll leave very cold water next to the ice. So that water has to be transported away, replaced with warmer water. So the amount of water motion below the ice is important. Surface area of ice that's submerged. Larger surface area, it's going to melt quicker. Wave action can break the ice up into smaller pieces with a greater overall surface area and thus faster melt. Waves will also mix the water, mix the warm and cold water, bring the cold water away from the ice that's melted and bring more warm water up to it. Okay, another big factor is export. For example, out of the Arctic Ocean through the Fram Strait between Greenland and Svalbard, a big factor for ice loss. Also into the Atlantic, say north of Svalbard into the Barents Sea, also through the Canadian archipelago, also possibly through the Bering Strait, although we don't generally see export out through the Bering Strait because the water from the Pacific is coming in. Okay, those are the mechanisms. And of course, any way that heat can get into the Arctic will increase the melt rates, whether it be from seawater, warm Pacific water coming in, warm Atlantic water coming in, jet streams being very wavy, bringing heat up into the Arctic, or bringing cold air out of the Arctic, which is effectively heating the Arctic as well. Mechanisms for sea ice formation, which is generally, okay, the sea ice loss, this is generally in the summers, okay, but the export can happen year-round and is. And I'll show you some data on that. Okay, mechanisms for Arctic sea ice formation. Seawater freezing onto the ice surface from below, the bottom surface, it thickens the ice. The seawater has to be at least minus 1.8 degrees Celsius or colder. That's the freezing point for 35 PSU salinity ocean water, typical ocean water. PSU, practical salinity units, parts per thousand. So 35 parts per thousand, that's 3.5 parts per hundred. We never say parts per hundred, we say percent, 3.5%. So heat radiates out to space, especially when there's no sunlight in the Arctic, cools the ice, cools the water below, causes freezing. Now ice is a good insulator. So the thicker the ice, the less heat loss from the seawater below the ice, and thus the slower the freezing of seawater onto the bottom surface. So if you look at ice freezing over time, it'll freeze very fast initially into ice, and then it will slow down exponentially because the ice is getting thicker. Precipitation, snow and rain or both falling and bonding onto the upper surface of the ice will thicken the ice. Also wave action, if you got a lot of seawater, washes onto the upper and side surfaces of the ice and then it can freeze. The more the wave action, bigger the waves, the more mixing there is in the water column. So if the water is warmer below this mixing, that reduces the ice formation rates. Okay, multi-year ice, okay, this is 5+ year old ice is the red. It's vanishing. Also, the 4-year ice, the 3-year ice, the 2-year ice is all getting less and less and less in the Arctic, being replaced just by 1st-year ice. Okay, so this just compares 2017 to 2016, and you can see the difference. Temperature in the Arctic basin, this is north of 80 degree latitude for 2016. This is the long-term average. This is what we're seeing. It's no surprise that the red line is dipping under the green because we're getting tremendous amounts of ice melt, and that's keeping the air temperature just above the surface of the ice close to 0. Look at these temperatures here, ridiculous. Okay, so this video, I'm saying if the overall trend continues, there's an extremely high probability that the first blue ocean event will occur by 2020 or earlier. The ice-free duration would likely be less than 1 month in September for the first blue ocean event. Now, this is talking about what I expect to happen after, and I'll do an entire video on my reasoning for this and also the other scenarios that could happen. We don't know for sure, okay? This is what I think will happen, but there are other things that can happen. I'll do a separate video on that. Okay. So let's get rid of this. And we'll get rid of this. Okay, Google WIPNEUS, W-I-P-N-E-U-S, or just type in this into a Google search and you get this page. And I'm going to explain the curves on here. Okay, so this is the PO mass. Okay, so the PO mass, it's getting the volume of the ice. So to get the volume of the ice, you need the thickness. The thickness can come from models, from satellite measurements. Obviously, it's much easier to measure area and extent than thickness. So here's the data is the black line. The red line is an exponential fit down. About 2022, this is the 95% confidence interval. The two extreme lines. Okay, two sigma lines. Okay, so 2021, summer of 2021, looks like the ice is gone from an exponential fit. You could do other fits. Okay, this is an exponential fit over the whole data from when the satellite era started. If you start, but it looks like this is super exponential, the curve. It's going faster than exponential. How do we see that? we start doing an exponential fit from the green point, the blue point, all these other points, and we get this envelope of curves. So if you do the whole data, you get 2021 in the summer, and if you take shorter intervals, you get gaps quickly. So 2017 is possible, 2018 is possible, 2019 depends a lot on weather patterns. This is from the exponential fits. Kaput, no ice, no sea ice. If you do a linear fit to this data, you know, you get longer periods of time, varying from 2026 to 2040, you know, 2032 or something. I don't think, you know, there's no reason, the exponential, this is the residuals, okay? So if you take the difference from the data to the line, this is what you get. So the residuals are actually smaller in this case here. This is a better fit than the other fit. Okay, but this is what would happen if it was linear, and there's something called a Gompertz curve, which kind of goes down and curves back up. We don't know a mechanism for this to happen, but this is the results that it shows you, and you can generate a family of curves by doing the same fitting at different points, and you get more like 2025 or so. Again, I think 2020 is the year, or before. If you take a bunch of different fits, there's an exponential fit is the red, and then the Gompertz fit, and then a log fit, polynomial fit, linear fit. You get numbers like this. Okay, this is based on the whole time period here, from satellite era to start. Okay, this is what happens on a monthly basis in the Arctic. So all of the months are losing ice. Okay, this is 2014. 2017 is here. Okay. If we look at the anomalies versus the 79 to 2009 average, this is 2017. What you see is there's less ice for the entire year, right? As we go on in time, there's less ice for the entire year. Okay, so this is the ice from January through end of December for 2017. And for 2016 is the red line here, and you can follow it for each year, and you obviously were losing ice volume throughout the entire year, from year to year. Okay, so that ends up where? At 0. Okay, this is interesting. It's the amount of ice volume that's transported through the Fram Strait, which is only one location where it's exported. And what you can see is, so this is the annual amount, so there's a bit less as we go from 80 onwards, little downward trend. There's less and less ice in the Arctic Ocean, so there's less to be transported. Okay, and then this is January, February, March is when most of the ice is exported through the Fram. And then this is April, May, June. There's less because there's less ice in the basin. July, August, September, there's not so much transport because the ice is in the basin and it's mostly melting out. And this is October, November, December. So October, November, December is pretty high export. And then January, February, March. But you can see it's dipping down here. There's less ice in the basin, there's less export. Okay, this is data. This is data through a year. So we've got 2017 here, so you can see how the curve goes. The export through the Fram really drops off in the summer. No surprise, because the ice has come back towards the North Pole a lot more. Okay, now this is the key thing. So let me go back to this curve here. Okay, this is an exponential fit going through 2020, 2020, 2021, 2022. But if I look at this, the family of curves, which is, where is it? This guy? This guy? Where did my curve vanished? Peel mouse. Okay, okay, where are we? Sorry for this little delay. There's my curve right here. Okay, so this is going down here. I showed you this. Okay, this is a family of curves. So the black is the data, and now we go here. So here's the black, now becomes the green here. That's September. So the question is what happens after the green hits 0 to the other lines? Thank you. Good morning, afternoon, evening, middle of the night, whatever time it is for you. Welcome. Dim the lights, get the popcorn, and step into this journey that I'm going to take you on into our very near future. In a previous video, I was talking about sea ice vanishing in the first blue ocean event in the Arctic Ocean by September, say 2020. So after that happens, whether it's 2020 or 2017 or 2022 or whatever, after the first Arctic blue ocean event, then what? What will happen, okay, to the ice after that? So I'm going to investigate the options and tell you what I think. I'm Paul Beckwith. I teach, usually I teach at in the Department of Geography at Ottawa and most recently at Carleton, but I don't have teaching positions yet. This work I do is all on my own time, and I just do it out of my concern for the planet. So if you want to encourage me to keep these videos coming and up the quality and get loads of different topics, then please consider a donation on my website, paulbeckwith.net. And suggest videos and I'll try to do it. You can see, you can have an influence on the videos I do. Okay, so let's try to answer this question. What will happen? Okay, maybe not. Technical error. Oh, I know. Okay, there we go. Okay, so here's my view, and if you've watched previous videos that I've done, you'll recognize this. I'll call it Scenario A. If the overall trend continues with sea ice, there's a high probability that the first blue ocean event occurs by 2020. Ice-free duration would likely be less than a month. Okay, the Arctic Ocean might be clear for a couple weeks or a month. There might be a little bit of ice around the edges, a little bit floating around, but essentially lost by 2020 or earlier. So then what happens? Well, I've said for quite a while, for years in fact, that this is what I think will happen, and I stay with this, but maybe it's wrong, but anyway, let's see. So ice-free duration would be extended to 3 months. So instead of the ice just being gone in September for a few weeks or a month in 2020, say, by 2021 or 2022, you'd have no sea ice for August, September, October. And then a few years after that, say by 2023, might have ice-free duration for 5 months. It might be June, July, August, September, October, or it might be add another month on 2 months before and after September. So July, August, September, October, November. So about 5 months of the year, about half of the year. Now, another scenario is that we stay in that state for a while, but I think we'll have an ice-free duration all year by roughly T plus 10 years, 2030 or so. And I'll explain why I think that in this video. Just one of the huge feedbacks is heat, okay? The Arctic's like a refrigerator. As long as there's ice, that heat goes into melting the ice. So the amount of heat that melts a kilogram of ice to 0 degrees Celsius, just above freezing, well, if the ice is just below freezing to just above freezing, it would raise the temperature. Take that same energy and put it on water at 0, it would raise that temperature to 80 degrees Celsius, a kilogram of water. This is a huge, huge effect. But there's many others. Okay, so first of all, people have pointed out, quite rightly, that, hey, you know, maybe the ice will stick around in the winter, maybe it'll just go in the summer. So these are the possible scenarios that I can think of. The Arctic Ocean ice-free duration, this is scenario A, which I think is going to happen. We get more and longer periods of ice-free duration until there's no ice throughout the entire year within a decade or so. I mean, maybe it takes longer than a decade, allowing other feedbacks to build up. Like if it takes some time for methane to come up big time, if it takes time for greenhouse gases to build up from cascading feedbacks, etc., you know, dwarfing human emissions, you know, and then maybe that would be required. But I think, you know, a decade or so for the sake of argument. If the scenario B could happen, things could proceed as in A, except you could reach some sort of quasi-steady state where there's an ice cover in the winter, which reforms in the winter, and the Arctic Ocean is ice-free in the summer months. So about half the year it's ice-free, about half the year it's got a perennial ice cover, which albeit would be very thin. You know, it would all be first year ice, obviously, and you know, kind of swirl around and stuff. But maybe it does reform each year. Okay, that's scenario B. Scenario C is that, well, it's a mixture of the two. You have the variability so large. Some years there's no ice in the summer. Other years there is ice in the summer. But, you know, maybe it reaches some steady state. So this is similar to B, until the greenhouse gases rise enough for it to completely vanish year-round as per A. So the timing, you know, first of all, you know, we have different ideas on the states, and also the timing from one state to the next. The progression of ice loss over time could vary. Other scenarios, let me know if in comments to this YouTube video if you think of them. Now, the mechanisms for Arctic sea ice loss, I covered this in a previous video. You have melting from above, melting from below, export out of the Arctic Ocean. There's lots of different things that are happening for each of these cases. So, you know, have a look. Just, you know, stop the video and read the slide, or watch a previous video where I explain this in detail. Mechanisms for sea ice formation, freezing onto the ice surface from below, precipitation, falling and bonding, wave action, overriding, bringing water over the ice which freezes, things like that. Again, I discussed that in a previous video. Okay, so now we get to the nitty-gritty of this video. Like I said, I think scenario A is most likely. As we get more science observations and more modeling, but not so much models, for me anyway, this view will surely change, of course. Okay, so it's the best I can do right now. And so here are some of the key points. With no Arctic sea ice after the first blue ocean event, the albedo of the Arctic will drop significantly. Now we've got the entire Arctic Ocean open, it's black, it's dark, it absorbs 90% of the incoming solar radiation, as opposed to the ice and snow, which could reflect, you know, 80 or 90%. So the seawater absorbs huge amounts of radiation, heating up to depth. No longer do we have a cold cap of water existing near the surface. The salinity is saltier water because we don't get that more ice melting. So it mixes with the salt water, so it's saltier and heavier. So the deeper North Atlantic derived water mixes with the sun-warmed surface water, keeps it warm for a longer period of time after the sun sets in the Arctic in the fall. The albedo continues to fall in the Arctic with the reduction of snow cover on the land, especially in the spring, right? And this is actually reducing even faster than the sea ice, and this will continue to, you know, put pressure on the ice not being there. Okay, another point. Wave energy greatly increases in an Arctic with no sea ice, obviously. You get wind going across large bodies of water now with no ice. It whips up the waves. You have a long fetch, or long distance of wind blowing across the water, long durations, and you get large waves. These large waves are there all year round, and they inhibit the growth of the sea ice. They break up any ice that's formed into smaller pieces. It has difficulty getting established. Okay, let's move on. The air circulation patterns will reverse in the Arctic. Okay, when there's an ice cap over the Arctic Ocean, the world that we're familiar with and we're leaving rapidly, the behavior is like that of a cold continent. You get cold air sitting above the ice. That leads to a high pressure area over the ice. The air moves from high to low pressure. Coriolis pulls it to the right, so we get a clockwise gyre. Beaufort gyre drags the ice along, and it leads to the transpolar drift. But when the Arctic has no ice, the seawater is much warmer than the land surfaces, especially in the fall. So the air will rise over the ocean, creating a low pressure over the water, and thus the surrounding areas are all cooling quickly in the fall, so that high pressure air is over there. Air moves from high to low pressure, curves to the right with the Coriolis. So we're going to get a air circulation pattern becoming clockwise around the Arctic Ocean instead of counterclockwise. This will draw warm surface waters into the Arctic Ocean from the open oceans north of Svalbard. It changes all of the patterns of movement, okay? And I think it will work to keep ice out of the basin in the Arctic Ocean in the winters. The Arctic Ocean region has ever increasing amounts of rainfall as it continues to rapidly warm, much less snowfall, even extending into winter. The water sources for many of these storms are from further south, as when that air moves up into the Arctic, it brings large amounts of heat up into the Arctic region. With the summer loss of sea ice, the refrigeration effect vanishes. Okay, I mentioned this already. The seawater rapidly heats up in the summer. It gets extremely warm in the summer, and it takes a long time to cool down because it's warm and it's mixed by the waves with warm water from below. And then when it starts, you get the radiative heating in the winter in a dark Arctic. Then there's still mixing of the water and waves, and there's an awful lot of heat that has to be removed before the ice can form. Okay, so when the ice is completely vanished in the summer, all of this heat goes into sensible heat. It accelerates the heating of the seawater. Okay, the jet streams. This is a key feedback. They become much slower and wavier. They're doing that now. The ridges go right up into the North Pole. We've already seen this. That will bring large amounts of heat to the North Pole, even in the complete darkness of winter. Temperature above 0 Celsius in the dead of winter in both December and February or March within the last 2 years. We've seen this already. Jet streams going right to the North Pole. They also go far enough south, they cross the equator. That's another topic, another video, and I need to revisit that from last year. This effect, I think, will be strong enough to ensure that the sea ice doesn't reform in northern winters of darkness. The jet streams normally act as a wall or barrier confining cold, dry air to the Arctic, warm, humid air to lower latitudes. Greatly warmed Arctic, these jet streams will be completely fractured, no longer exist as a wall. There's nothing stopping the warm, moist air from lower latitudes carrying latent and sensible heat directly up to over the Arctic Ocean throughout the entire year. And cold, drier air from the Arctic region can move southward. No jet stream wall or barrier. So both of these types of transport, if you have cold air moving to the Arctic, or if you have warm moist air moving to the Arctic, that's bringing heat to the Arctic. If you have cold, dry air from the Arctic moving south, that has to be replaced with hotter air that also warms the Arctic. Both effects warm the Arctic. Okay, after the first blue ocean event, ramping up of warming in the Arctic will greatly increase Arctic temperature amplification. Greenland's exposed. Melt rates of Greenland glaciers will accelerate with corresponding acceleration of global sea levels. Rising sea levels will cause calving and loss of Antarctic glacial ice, and they'll both be shedding ice, and that further raises sea levels, which then will mix into the Arctic, and you know, it'll cause yeah, I think it also adds to no sea ice year-round. Much warmer oceans in the Arctic will increase evaporation levels. Much warmer air in the Arctic carry much greater amounts of water vapor. You know, remember, a 7% increase in water vapor occurs per degree Celsius rise in temperature. That's what the air can hold. This evaporation from the Arctic Ocean water will continue into the fall, so there'll be much thicker and more extensive marine cloud cover layers formed. Okay, these clouds will continue into the winter, and they trap long-wave radiation, so it won't be able to boot off into space. It'll be trapped, so the Arctic will be warmer, sustaining the water instead of ice. Greenhouse gas emissions will add lots of CO2 and methane into the Arctic from terrestrial permafrost. It takes time for these gases to diffuse southward, so they'll greatly increase warming in the region. Now, also, I discussed the Russian observations over the eastern Siberian Arctic shelf recently. There's an ever-increasing amount of thaw of subsea permafrost. So therefore, you know, the permafrost is like a cork on a champagne bottle, so the emissions of methane from clathrates and free gas in the sediments will skyrocket. There's a risk of large methane releases, greatly multiplying the methane. So we're in a global climate emergency. It's thus far ignored and essentially unrecognized by society. We have to declare an emergency, and then governments all around the world and people and policymakers can respond. And we need to deploy the three-legged bar stool, which I illustrate here. Okay, there's a great book, Drawdown. Have a look at it. Good morning, evening, afternoon, middle of the night, whatever time it is and wherever you are. Welcome to the evolving story of our Arctic and the ongoing changes and impacts that every human on this planet will face. So, 2 videos ago, I argued that the Arctic sea ice, oh, by the way, you know who I am and you know where I am and what I'm affiliated with if you've watched any of my other videos, so I'll just skip that part. So, a few videos ago, I argued that we're going to lose Arctic sea ice in the summer for the first time in a blue ocean event by 2020 or earlier. In the last video, I contemplated what would happen to the sea ice after that event in subsequent years. And the scenario that I'm leaning towards thinking will happen is that we'll just continue to lose the sea ice for longer and longer durations until it's gone year-round within about a decade. Other people argue mostly that the radiative losses from much warmer Arctic will be super high as soon as the sun goes down for those 6 months of darkness in the Arctic, and the sea ice will reform during that period. That would lead to a scenario where there's sea ice in the winter months and no sea ice in the summer months. So let's have a look at some of the rationale between some of these arguments, these other views that the sea ice will always have sea ice in the Arctic at some point in the year. Yeah, let's see what there is in the literature. And there's very little modeling's done on this, and this is becoming more and more urgent, obviously. So Google Wipneus, W-I-P-N-E-U-S, and it takes you to here, or just type in this name and Google this, you find this image. This is up-to-date images showing the sea ice thick volume decreasing here. If you fit an exponential curve to it, summer of 2021, with bands here, 2 sigma bands, deviation or variability bands, 95% confidence that will be in between those curves from this variation here, fluctuation. If you change your fit, instead of fitting an exponential to the whole data, you fit it to subsequently more recent data. So this is showing that the curve is actually falling steeper than exponential here, and then you get a spread of values. So I'm arguing 2020 or before for loss of sea ice volume going to 0. This green curve at the bottom is the black curve, so it's for September. Bracketing it here, we have August and October months. So I'm arguing that when this hits 0, these will be dragged to 0 quickly. Now, of course, there is an argument that when the first curve goes to 0 in September, everything changes and the trajectories of these curves may change. So there is an argument, and I'll have a look at that. So one of the things that is key is our planet is changing completely. Okay, the temperature difference with latitude is greatly decreasing. So this is, look at all this water. This is total precipitable water moving up from the equator towards the poles. And look what's happening right now over large parts of the US and Canada. It's just, we're being fire hosed. Okay, precipitation. We had over an inch of water in Ottawa, which is 45 degrees north latitude. Yesterday. We had over an inch of water today. We're having over an inch tomorrow for Canada Day ceremonies. Look at the water moving up here. So as the jet streams become wavier, we're getting water going up to much farther distances. The jet streams are actually going up to as far as the North Pole from time to time, bringing water vapor and heat up there. So we're getting a tropicalization of the northern hemisphere as a result of the jet streams first getting slower and wavier, and then ultimately they're heading to collapse, breaking the wall, allowing water vapor to head right up into the Arctic. keeping it warm there year-round is one of the arguments I'm making. This is a so-called death spiral. This is September is the black line. Everything's circling closer and closer to zero. When the black line, September, goes to zero, no sea ice volume. And then that pulls a few other months down. And this is, I'm looking at some different views on what else can possibly happen. So here we go. If you Google Scholar, go on Google Scholar, so it just gets peer-reviewed, published results. I also put since 2017 just to get the most recent stuff. And I get a bunch of different papers here, some of which I'll look at. The most interesting is after the ice goes. Have a look at that. I'm not sure if it's behind a paywall or open, but I'll be discussing it here. So, first of all, this paper here, influence of high latitude atmospheric circulation changes on summertime Arctic sea ice. So it's always good just to look at the abstract here. So the Arctic, rapid sea ice decline in the Arctic for 3 decades, warming at twice the global rate. The relationship between warming and sea ice loss, not well understood. Well, really, not well understood. I mean, it gets warmer, you lose sea ice. But anyway, that seems to be understood. But anyway, talks about the different circulation patterns and some modeling and different trends and things going on. Often it's good just to look at the figures. So let's go down and see some of the figures. So things like this is 1980 to now. This is the sea ice loss, is the blue line. We've got the specific humidity rising, getting a lot more water evaporation in the Arctic, a lot more water carried up into the Arctic, bringing latent and sensible heat. So the humidity is rising, the temperature is rising. Long wave radiation going out to space is also rising because the Arctic is warmer, and in the winter it'll radiate more heat out to space. Okay, so we get different curves like that. I'm not going to go into all of the details here. What does the conclusion say, if I can see? So it does a lot of modeling. There's a lot of technical stuff here using GCMs and stuff like that. Okay, so we read the abstract and we looked at some figures. So that's the gist of the paper. This guy here is a stochastic dynamical model. So how the Arctic sea ice is changing. Theoretical physics guys, math guys, Cambridge and Yale. So, look at the abstract. There's noise in the system. There's a lot of variability. Okay, as a system is about to change a state, then there can be a critical slowing down of frequencies leading to larger excursions in both directions, so more variability. And they're trying to look at this from a mathematical point of view, and they're comparing it to different examples in stochastic dynamics. So noise is multiplied, and you get various things happening. I don't want to dwell on that paper. This is a poster that was at a conference, and there's a couple interesting things in here. Impacts of climate change, sea ice loss. One of the things is relative to pre-industrial. These are some temperatures. We've gained a degree since 1890. In the Eemian, when we were a degree higher, the sea levels were 6 to 9 meters higher than they are today. 1 to 2 degrees higher 400,000 years ago at a strong interglacial, 6 to 13 meters higher. 3 million years ago, Pliocene, much, much higher and 2 to 3 degrees warmer than today. This is an interesting image here. This is showing so the black is the sea ice percentage coming down, the sea ice dropping down, and the green is the total sky albedo. So from the sky, looking down on the Arctic, including the clouds and everything else, that's the albedo. So we're seeing a decline in albedo. This is the 52% down to 48% as measured by the Ceres satellite. And then we have the temperature anomaly is the red line here going up. And this would be the temperature anomaly for the Arctic. Here we have clear sky albedo. So if there's no clouds, the blue is the albedo dropping due to the sea ice going. And when you incorporate the additional clouds, the sea ice is going, there's more evaporation, there's more clouds, you can see the total sky albedo dropping, you know, because of the cloud effect. The cloud effect is the difference between the green and the blue line. So we can see things like that there. This is variations in the albedo and the link to seasonality of sea ice. You know, so the Arctic's warming 2 to 3 times faster than the global average. There's modeling and stuff. Let's have a look at the crux of the best one I found on this. I want to spend a bit of time. So this is the Arctic, you know, a bit of ice, mostly snow, mostly water in between. After the ice goes, researchers look into the Arctic's future for clues to save species and maybe even bring the ice back. So this is a fairly recent paper in Nature. So basically it's talking about the twilight zone. In the space of a few months, the Arctic was very strange last year. After autumn, 20 degrees Celsius above normal temperatures, huge amounts of water vapor there. The Arctic is quickly reshaped. They say it's the summers that have scientists worried. As early as 2030. Wow, 2030. I'm arguing 2020, okay? So this is in Nature. This is sort of a mainstream view. I'm always the outlier anomaly. That's fine. I don't mind being an anomaly. 2030. How did they get 2030 looking at the graphs? I could get my 6-year-old kid to say, draw a line when this goes through 0. Actually, I don't have a 6-year-old kid. This was a joke I used to use 10 years ago. I could get my 16-year-old kid, no longer a kid. Anyway, a blue Arctic Ocean could amplify warming trends, scramble weather patterns. It's doing it, obviously. They should really quote me in all of this stuff. I've been talking about this stuff for 7 years. Okay, other scientists need to, okay, so let's look at some of the key things in here. The blue period. It's not this irreversible process. You could bring it back even if you lose it all. I mean, they're arguing that by cutting emissions, the Arctic could eventually come back. We'll lose sea ice. It'll be gone in the summers. It'll probably come back in the winter, be there in the winters, and so on. Okay, so there's different models, but we know the models are all underperforming. So here's some of the things that's happening here. Because of circulation patterns, summer sea ice could survive in Greenland and Canadian Arctic after it disappears elsewhere. I don't think so, and I've explained in detail why in my last video. You know, they talk about, you know, ideas to bring the ice back. So they're starting to talk about global cooling and geoengineering, but many researchers hesitate to embrace it. Well, we'll see if they hesitate. Come 2020, there'll be a mad scramble to deploy solar radiation management and the three-legged bar stool that I'm talking about. Remember, I've been arguing forever that there's a climate change emergency. So basically, they did some modeling here. They said that there's a threshold. So if you go above this threshold, then the sea ice is gone year-round. So for example, they increased CO2 in the model from 280 to 1100 ppm, and they found that the ice, that would obliterate both winter and summer sea ice. Okay, then they reduced CO2 concentration so that when the to see when it would return in the summer and winter, and they did that sort of stuff. But you know, I'm sure that there's all kinds of things that are missing in their models. I think we can do a better job of trying to figure out what's going on. They then talk about some ideas of global cooling, in other words, large-scale geoengineering, like I say, to cool the Arctic, to return to a world with summer sea ice. Could have big perks, such as, yeah, like saving humanity. They don't say that, such as restoring some of the climate services that the Arctic provides and stabilizing weather patterns. Okay, restoring a white Arctic could offer relief to polar bears, blah, blah, blah. Okay, most researchers think the Arctic may have been had ice-free summers during the last interglacial 130,000 years ago. Let's hope that it did, and let's hope that some of the methane on the eastern Siberian Arctic shelf was released during that time period and contributed to the warming and is no longer there for warming to be released for us. Okay, regrowing sea ice. Yeah, so basically the gist of this paper is that at present CO2 levels, the sea ice will be there in the summer and gone in the summer and there in the winter. Thank you.